Good evening. This is the live session for Polymer Reaction Engineering. This class is a review class and we'll be seeing some old assignment problems and going over some lecture topics just for review and revision. Starting from classification of polymers. You know that polymers are large macromolecules consisting of repeating units called monomers arranged in various ways. That is the basic definition for polymers. So classification of polymers can be done on various bases. uh, we have starting from based on the reaction mechanism from where they come from. That is nothing. That is how we define addition polymers and condensation polymers. Addition polymers are polymers where the chain grows as the double bond in the monomer is broken and the monomer polymerizes to form addition to undergo addition polymerization reactions. So examples for these would be polystyrene and polypropylene, very popular polymers, which are widely used in uh, everyday applications. Next is condensation polymers. Condensation polymer is actually a straightforward polymerization process where monomers polymerize and release small amount of byproducts. Byproducts in the sense like water or any other byproduct, which occurs when condensation polymerization happens. Examples for these would be nylon and PVT. Again, very widely used products uh, in everyday applications and household purposes. Next, we have based on the molecular structure. Now, in polymers, then we are defining them based on molecular structure, have several types. First is linear chains. Linear chains contain long straight chains of polymers without any branching. Basically, they are entangled with each other and can have a high degree of crystallinity. So based on that, the linear chains are defined. Example for this would be high density polyethylene, polystyrene, or ultra high molecular weight polyethylene. Ultra high molecular weight polyethylene, which has long straight chains which are entangled with each other. Next, next classification based on molecular structure would be branched chains. Branched chains are, as you can see right here, a kind of branching right here. You can see the main polymer on the main polymer backbone, there are small groups coming out here, as you can see branching. Secondary groups are attached to the main polymer backbone. So that is defined as the branching polymers. Next, based on molecular structure, we have network or gel polymers. Network or gel polymers, they are formed by crosslinks between the straight chains and they cause the polymers to have different properties. So if you take two straight chains like these, or you can take this branch chain or this straight chain and try to cross-link them to form a network or a kind of gel-like structure that will have different properties. So based on that, your network or gel polymers are formed. An example for this would be vulcanized rubber and polyacrylamide. In vulcanized rubber, what happens is that the neoprene and isoprene which are there, which are present, they are vulcanized or cross-linked together by adding addition of sulfur, and this sulfur creates the vulcanization rubber. And this rubber has different properties than your standard rubber. It is very hard and it's basically used for manufacturing of the tires. So classification of the polymers based on molecular structure will have linear chains, branch chains, network, or gel polymers. Moving on, next we have morphology. In morphology, we have two types: amorphous polymers or crystalline polymers. Amorphous polymers and crystalline polymers. In amorphous polymers, they remain in a glassy dry state below their glass transition temperature, and above glass transition temperature, they become rubbery in nature. So these are the amorphous polymers. Next we have Crystalline polymers. Uh, Crystalline polymers are rigid in nature and more and have a higher melting point. So crystalline nature of the polymer makes them strong. Some example would be nylon, polypropylene, uh, nylon and polypropylene. And for the amorphous polymers would be polycarbonate. You can see that in amorphous polymer, the structure is disarranged like this. And in semi-crystalline polymers or crystalline polymers, the polymer chains are tightly packed and arranged in a linear order, properly arranged. Next, we have based on the molecular composition of the polymers. Molecular composition of the polymer, based on molecular composition, we have homopolymers and copolymers, and block copolymers. Homopolymers, we have same repeating units, same repeating units. That is your normal polymer. It's called a homopolymer. On next, we have copolymer, where there are two or more different monomers constitute the polymer chain. Two or more monomers can be attached onto the polymer chain. As you can see, alternate here, you can see the copolymer structure, alternating, random. You can see the main polymer backbones having this pink colored repeating units right here. In random arrangement, these pink colored repeating units are appearing at irregular intervals in the backbone. And next, we have block copolymers where alternating blocks of different polymer molecules are linked onto the polymer backbone. As you can see, the two pink blocks right here, they are present at regular intervals on the backbone. And another type would be the graft polymer, where these uh, copolymers are attached as grafts onto the main polymer backbone. So that is the classification based on the molecular composition. Next, we have based on the temperature response. Temperature response for polymers consists of two of them, thermoplastics and thermostatic plastics. So thermoplastics can be easily melt with increasing the temperature and can be remolded, and they can undergo repeated cycles of heating and cooling without having much difference in their properties. Standard example for this would be polypropylene, polyethylene terephthalate, and polyethylene. Next, we have thermosetting plastics. Thermosetting plastics, they do not melt, and instead of melting, they have such a hard crystallized structure that they straight away go for decomposition. So they decompose at very high temperatures, and they cannot be remolded once they have been set into a mold. Thermosetting plastics are usually formed by adding some kind of cross-linking agent to a native polymer. So when you add the cross-linking agent to the polymer mixture, it starts to form a network, which gives a highly sturdy property to the thermosetting plastics. Common example for this would be bakelite. Bakelite is a polymer which every household switch has it. As you can see, it's formed with bakelite. It is used in electrical appliances because sometimes in electrical appliances, if the temperature goes very high, bakelite is easily able to withstand high temperatures and does not deform. Moving on to the next topic. Uh, the next topic in the polymers, there are different kinds of forces which which create the polymer backbone and different kind of functional groups which are attached to it. So based on that, we have two statements here. Polymer molecules are attached to each other with primary and secondary bonding forces such as covalent bond, ionic bond, hydrogen bonding, and van der Waals forces. So the primary force which attaches the polymer together is the covalent bond. So the monomer molecules are attached with each other through covalent bonding, and ionic hydrogen and van der Waals forces are the secondary forces which exist within the either within different chains. So as you can see right here, this molecule, this long chain polymer molecule, you can see one, two, and three chains are there. And you can see the hydrogen atoms which are present here are forming hydrogen bonds. So hydrogen bond is a secondary force, and the covalent bond which is formed inside the chain itself is your uh, primary force. So, and the second statement is covalent bond forms when the difference between the electronegativities of two atoms is too small for an electron transfer to occur to form ions. So, as you can see, carbon-carbon, whenever they share atoms, they form covalent bond like this. So, both of the statements are true. Statement one and statement two are true. Based on this, you can see. Next question we have the correct sequence for dissociation energy of bonding forces in polymer structure is covalent bond, ionic bond, hydrogen bond, and dipole forces and van der Waals forces. So as you can see that the main polymer structure's backbone is formed with covalent bond. So that's why the dissociation energy of the covalent bond will be the highest. And moving on to the next one, we have ionic bond. Ionic bonds, the formation of ionic bonds are happens because of the lone pairs of electrons where ionic activity is very high. So because of that, they will have second most highest dissociation energy. Next, we have hydrogen bonding, which exists like this between hydrogen molecules which are present on the sides of the main backbone of the polymer. Then dipole forces, and then the weakest ones that are van der Waals forces. So this statement is. Moving on to the next question, we'll be coming across one of the most important properties of a polymer, that is the molecular weight distribution of the polymer. So you can see a curve right here which describes the weight fraction versus the molecular weight of a polymer. So polymers always usually have a range of molecular weights because uh, during the polymerization process, no two chains are equal. It is actually desired to have all chains of equal length, but that cannot be actually done in real cases. So that's why we try that always the polymerization reaction occurs in such a manner that majority of the chains contain this similar kind of weight. So as you can see this curve right here, we have first Mn, Mv, Mw, and Mz. So based on this nomenclature, different molecular weights are distributed, and based on their weight fraction, the entire molecular weight of the polymer can be studied as a distribution. So Mn is your number average molecular weight. Number average molecular weights usually depend upon the number of the polymer chain, the number of the polymer chain which is present in the largest quantity. So, example, if you have six chains, like among these six chains, four of them have a weight of 20 gram per mole. So these four chains will be the one which will guide the weight of the polymer under number average polymerization nomenclature. Next, we have viscosity average molecular weight nomenclature. Viscosity average molecular weights are defined basis on the solubility of a polymer in a certain solvent system. So based on that solvent system, you will be defining its molecular weight. So if you have a polymer which dissolves differently in, let's say, PCB, that is trichlorobenzene, or THF, that is tetrahydrofluoride. So based on that, the the extent to which the polymer is able to dissolve in these will guide how the it will guide how the polymer is having its weight determined based on these two solvents. Next, we have MW. Next, we have MW. MW is your weight average molecular weight. Now, weight average molecular weight is defined by the polymer chain which is having the highest weight, and in the entire polymer mixture, any polymer chain which is having the highest molecular weight and the number of those chains having the higher molecular weight, based on that, you determine the weight average molecular. And on top of that, when you divide weight average molecular weight with number average molecular weight, then this ratio will give you the breadth, basically the breadth of this distribution. That is nothing but your polydispersity index. So the polydispersity index, its definition is uh, the ratio of the weight average molecular weight by the by the number average molecular. So that will give you the polydispersity index. Now, any polymer having a polydispersity index of 1 will have a molecular weight distribution which will only spike at one weight, one molecular weight. So the entire polymer, monodisperse polymer, any polymer having a PDI of 1 is called monodisperse, and any monodisperse polymer can be defined from a single molecular weight. So that single molecular weight will be the determining weight of the entire polymer. But in real cases, no polymer can be monodisperse. As we just discussed that polymerization rates and degree of polymerization is very difficult to control. So because of that, the polymer will not have a monodisperse the polydispersity of 1. So because of that, this ratio is very important in determining the breadth of the molecular weight distribution. Lastly, we have something called MZ. MZ is the molecular weight of the polymer based on its longest chain, which forms during a polymerization reaction. These chains are chains which are present in very low numbers, and these chains are present in very low numbers, and these chains are formed because of excessive propagation step or improper termination of the polymer, where the chain growth exceeds a certain point. So at that time, NZ is defined. Moving on to the next question. Next section will be defining some basics about chemical kinetics. So we have what is the slope of the plot of ln K versus 1 by T for a reaction where the activation energy is positive for temperature dependency of reaction rate constant given by the Arrhenius equation. So we know the standard Arrhenius equation, what is defined by K is equal to K naught into E power minus activation energy by gas constant into temperature. So based on that, you can see right here there is a diagram which shows how when the energy increases and how the reaction coordinate moves forward. The reactants move forward, reactants gain energy, and once they reach the activation energy, they form the activated complex, and then the activated complex moves on to give the product. And the products are present at a different energy level than the reactant from where it started. So in this case, we can see that the plot of ln K versus 1 by temperature for a reaction where the activation energy E is positive, for the temperature dependency of reaction rate constant given by the Arrhenius equation would be minus E by R in this case, because as we can see that the standard Arrhenius equation describes the entire equation as K is equal to K naught into E power minus EA by RT. So in that case, even if the activation energy is positive, you will have the entire term as E by R. So the slope is given in that respect. Moving on to the next one, we have something related to parallel reactions and multiple reactions. For different types of multiple reaction systems, select the correct statement. First, we have in a parallel reaction system, the reactants are consumed by different reaction pathways to form the different products. In series reaction systems, the reactant is consumed to produce an intermediate product which reacts further to produce the final product. In a complex reaction system, both parallel and series reactions are involved. So let's take a look at the first statement. In a parallel reaction system, the reactants are consumed by different reaction pathways to form different products. So here is an example. You have a reactant A which is undergoing a reaction to form B and C, which is having different reaction rates, rate constants. You can see K1 and K2 right here. So this is a parallel reaction system where A forming B and A forming C are competing with each other, and with respect to that, K1 and K2 are defined. So in a parallel reaction system, the reactants are consumed by different reaction pathways to form the different products. So this statement is true. Next, we have in series reaction systems, the reactant is consumed to produce an intermediate product which reacts further to produce the final product. So you can see that in a series reaction system right here, A given B given C, there are two rate constants defined. So A is first transforming to B, that is nothing but your intermediate product. This is the middle step. So that's why it is forming a intermediate product. So that reaction rate constant is defined as K1. And then this intermediate product might react further with a rate constant of K2 to give the final product C. So this statement is also. Then in a complex reaction system, both parallel and series reactions are involved. So complex reaction system, the definition of complex reaction systems is that no elementary reactions are involved in that, and uh, anything other than elementary reactions when they are involved, we can call them that it's a complex reaction system. Both parallel and series reactions can be involved in a complex reaction system. So all of the above is the correct answer. Also, you can see this graph right here that for the same reaction that as time proceeds, the reactant gets consumed. As you can see, the reactant gets consumed and the concentration of B and C parallelly increases. But as you can see, the concentration of B is higher than C and C is already reached its maximum and is on a further decline. You can tell that in these two competing reactions, the selectivity for B is higher than that of C. So that's why this reaction system is defined through this curve like this on a concentration versus time basis. Next, we'll be seeing a topic in chain polymerization, radical chain polymerization, and how this phenomena affects the polymerization rates of the process. We have the chain transfer process. Chain transfer process is defined as the polymerization process by which the activity of a growing polymer chain is transferred to another one. So in straightforward terms, we can see that we have a chain group of chain. We have a chain here. When it interacts with the A molecule, right here, the monomer, it transfers its activity, growth activity, to the other chain. So that is the basic definition of chain transfer polymerization, where the activity of a growing polymer. For example, you have a monomer which is growing, adding more monomers to it and forming a long chain. It halts itself and passes on that activity to another monomer or another chain, another molecule basically. So chain transfer process is a process by which the average molecular weight of a polymer might reduce. Why? Because during a chain transfer event, what happens is you are basically giving away the activity of a polymer chain onto the other. So you are halting its monomer addition. That is nothing but your polymerization reaction for that chain. So the molecular weight remains limited. And that's why, and as the activity moves on to the next molecule, there is no guarantee that the next molecule might undergo a similar polymerization rate as the previous chain. So that's why the average molecular weight reduces in case of a chain transfer process. Chain transfer can occur by itself or can occur by itself because of formation of some unwanted byproduct or can be introduced deliberately into a polymerization reaction by adding addition of chain transfer agents. Chain transfer agents they halt the growth of growth and polymerization in a single monomer molecule and pass it on, or either pass it on or take it on to themselves to halt the polymerization in that particular molecule. So chain transfer process occurs in addition polymerization, radical polymerization, cationic and anionic polymerization. There are different types of it. First type is transfer to agent. The chain transfer agent, when the activity of the growing molecule is transferred to the chain transfer agent itself. So the transfer agents have at least one weak chemical bond, which facilitates the chain transfer reaction. So because of that, the transfer to the agent occurs. Next type would be the transfer to monomer. So we have a monomer, like if we have a monomer, what happens is the growth of the uh, initial polymer will halt and pass that activity onto that monomer. So growing polymer chain breaks an atom from the unreacted monomer existing in the reaction medium and then gives it onto the monomer. This usually determines the molecular weight achieved by the monomer. So as I said earlier, that as the activity moves on to the next monomer, that will determine its weight, and you can define the average monomer weight based on this. Next, the transfer is to transfer to polymer. So what happens is uh, the activity can transfer onto a monomer or onto another polymer chain. So occurs, and this occurs usually at the end of a radical polymerization reaction, and all monomers are consumed. So if there are no monomers to pass on the activity to, this activity will move on to the polymer chain, which has formed at the end of the radical polymerization cycle. And lastly, the transfer of the activity can occur to the solvent itself, and solvent can act as a chain transfer agent. And in that case, what happens is your solvent itself will halt the uh, progress of initial polymer chains and pass on the activity to other polymers. Or we can see the question right here. From chain transfer polymerization, we move on to the next topic, that is the ionic polymerization. So, for a compound to act as a good cationic polymerization initiator, the following properties are required. These are the correct options. It should be highly nucleophilic compound. It should be a strong acid, example hydrogen fluoride, or it should have electroinitiation in possible is possible where either the monomer, solvent, electrolyte, or any other added species can initiate the process via electrolysis. So, in case of cationic polymerization initiator, it cannot be highly nucleophilic compound, since nucleophilic compound initiators are usually used for anionic polymerization process, and it should be a strong acid. Uh, strong strong acids such as hydrogen fluoride are not desired in that case. And next we have electroinitiation is possible where either monomer, solvent, or electrolyte or any other added species can initiate the process by electrolysis. So what happens is that uh, the need for cationic polymerization is to generate a cation which will initiate the polymerization reaction. So any kind of electroinitiation step where either monomer, solvent, or electrolyte can undergo electrolysis and initiate it by creating a cationic species which will start the polymerization reaction is usually desired. So this is the correct option. So based on that, we will be looking at cationic and anionic polymerization processes. So in anionic addition polymerization process, what happens is that addition polymerization of monomers is initiated basically with a anion. So the anions, how they initiate it is by electron transfer, first of all, where the radical anion transfers itself onto the monomer, and because of that, the polymerization process initiates. Polar solvents are basically a very much important aspect of this because polar solvents maintain the stability of the anion radical, and they help to solvate the cation species and suppress them. So basically, anion species remain stable in that case, and that's why it is very important. Next step, and next step is the anion radical transfers to the monomer. So once the initiation occurs, the anion radical then transfers onto the monomer, and then the polymerization process begins. Next initiation is by strong anions. The presence of nucleophilic initiators, which include covalent or ionic metals, amides, hydroxides, or cyanides. As we've seen in the previous question, that it should be highly nucleophilic compound. So, as I said, it won't be good for a cationic polymerization. It will be good for an anionic polymerization. So, nucleophilic species, which which includes covalent or ionic metal species such as amides, hydroxides, or cyanides, are very helpful. As you can see right here, there's an amide group right here, and that is very helpful in initiating the anionic polymerization process. And during the propagation step, what happens is that all the monomers are completely consumed. So as the anionic polymerization proceeds further, what happens is that all the monomers which are initiated in the first stage get consumed. Sorry, all the anions which are attaching onto the monomers in the first stage consume the entire monomer and make them undergo polymerization process. Next, to terminate the reaction, there are different methods. First is by quenching of the impurities, because anionic polymerization sometimes undergo a term called living polymerization process. In living polymerization, what happens is that the ability of the polymer to terminate itself gets suppressed or gets completely removed. This happens because either the chain transfer rate is absent, basically no chain transfer is occurring, and all the process parameters are favoring the growth of the polymer. Either that is occurring or initiation rate is very larger than the propagation rate. So if the initiation rate is very larger than the propagation rate, what happens is lot of monomers will go under initiation and they will keep initiating the polymerization process again and again. So in that case, the kind of polymerization is called something called living polymerization. So in such cases of anionic polymerization process, what you have to do is quenching can be performed by addition of some impurities. What happens is you add some impurities to quench the polymer reaction and stop the polymerization process as it is. So in that case, you add some impurities and the polymerization process gets halted. Next is intentionally allowing introduction of some tailored end groups. So by intentionally allowing some introduction of tailored end groups, in that case, what happens is uh, your entire anionic polymerization process will get halted as the tailored end groups will move on to the any kind of anionic species and suppress them so that the polymerization process gets halted. Next, so these are the steps for the anionic polymerization process. Next, we have the cationic polymerization process. Cationic initiator its initiation process is similar as that of the anionic polymerization, wherein that the cationic initiators transfer charge to monomer, and then from then on, the polymerization process occurs. So in the initiation step, the class usually protic acids are used. You can donate protons to the monomer, and then form a cationic initiated monomer, which will then undergo polymerization process. So usually strong protic acids can be used to form cationic species of the monomer, which will undergo polymerization process. That was the first type of initiator. Another type of initiators are something called Lewis acids or Friedel-Crafts catalysts. Lewis acids are usually defined as empty orbitals which are capable of accepting electrons. So one example of that of this and the Friedel-Crafts catalyst will be tin chloride and aluminum chloride. So these can be used to initiate the cationic species onto the monomer, which will then undergo propagation. Other than this, there is another method by which you use ionizing radiation to ionize the monomer itself and create a cationic group there, and then that will be used, that will initiate the reaction. So based on this, the initiation occurs. Now moving on to the next one, that is the propagation step. In the propagation step, what happens is that addition of the monomer to active species, addition of the monomers to active species occurs. So what happens is the leftover monomers, they go and attach themselves onto the active species where the cationic body is present, and addition of more monomers on top of that will give you a growth of the chain. That is, the propagation will occur. On top of that, this is usually done in a manner of head to tail fashion, that these monomers are attached onto the cationic group by head to tail orientation, and then the cationic end group is regenerated. On top of that, the cationic end group is always regenerated. So this will help in propagating the polymerization process even further. And during this process, temperature has a very important role to play, as the rate of initiation, the energy required, energy required for propagation and initiation is always less than that of termination. So in that case, if you reduce the temperature, your propagation step or the energy required for propagation will increase, and then propagation will occur faster at low temperatures. That's why cationic polymerizations are often carried out at low temperatures, so that propagation step is favored and high molecular weight polymers are generated. So that's why temperature has an important role in controlling the rate of the cationic polymerization process. For termination of the cationic polymerization process can occur in two ways. First is unimolecular rearrangement of the counter ion. So, in presence of any kind of counter ion, which is countering the effect of the cation reduced cation and group, the cationic end group, when it comes in contact with the counter ion, will undergo unimolecular rearrangement, which will terminate the entire poly polymerization process. So, as the counter ion will neutralize the cationic charge on it, it will undergo a unimolecular rearrangement, which will stop the cationic polymerization process. Another one is that anionic fragment of counter ions combines with the propagating chain end. So similarly, in that case, anionic fragment of the counter ion combines with the propagating chain. So any kind of propagating chain, when it comes in contact with the counter ion, the anionic end will attach onto the cationic end, and then that will result in halting of the polymerization process. In these cases also, in cationic polymerization, chain transfer also can occur in two ways. Both ways include hydrogen abstraction, where the activity from one propagating chain can move on to the next one. So, in the first hydrogen abstraction case, what happens is the active chain passes on its activity to the counter ion itself. So, the cationic group is lost onto the counter ion, and because of that, it will lose its activity. In the second case of hydrogen abstraction, what happens is the active chain will lose its activity onto a monomer. You can see right here that the active chain will lose its activity onto a monomer, and because of that, the chain transfer process will occur. So that's how it will also result in movement forward to the termination of the cationic polymerization process. So uh, I hope you have uh, reviewed some of the ionic polymerization, chain transfer polymers, and basic polymer properties basics with this lecture. And I will say that all the best for your exams. And I hope all of you have completed your assignments and would be well prepared for the upcoming exams. Thank you very much.